We're going to start the next chapter, chapter 16. And what chapter 16 deals with is functions of several variables. Now, we've been looking at the last time we really dealt with functions, we were dealing with functions that we can study just in the plane. So, for example, we were looking at something like, the square root of x minus 1, something like that. And this is a scalar function. It's not, we study vector valued functions where we put in a real number and get out a vector. This, we just put in a real number, we get out a real number. And remember, what we're concerned about with a function like this is, of course, what the domain and what the range is. And for this one, it's easy to determine the domain. Remember, what we were worried about was that we not try to take the square root of any negative number. We can take the square root of 0, that's fine, but not a negative number. So we would say the domain is x greater than or equal to 0, or we would write it 0 to infinity, like that. Yeah, 1. So this is 0, and this is 1. And then here we got a 1 right there. Okay, so this is our domain. Now, with vector value, with functions of several variables, and by the way, if we wanted to sketch what this looks like graphically, it was very easy for us because we know this is the square root function. It's been shifted 1 to the right, and it looks something like that. So we've gotten in the habit of being able to deal with functions by just by looking at their graphs. In other words, I can look at this function and look at its graph and immediately know something about the behavior of the function. Well, when we get to functions of more than one variable, this becomes a little more challenging, looking at the graph and dealing with these functions. So let's just start off looking at a function here. Now, here, like that function up there, we put in a single number and we get out a single number. Here, we're going to put in an ordered pair, and we're going to get out an ordered pair. So let's just suppose this is a function, f of xy. What we're going to do is we're going to put in an ordered pair and get out a real number, I should say. I think I said we get out an ordered pair. We put in a real ordered pair and we get out a real number. So here's what it's going to look like. If you, let's just suppose I have the, an xy axis here. And let's suppose that the domain of this function is just, something like this. Let's suppose this is the domain. Now remember, when we were dealing with one dimension or two dimensions, we had the domain in terms of x, and we said, well, x, and it was just one dimensional, right? X goes from point A to point B. Well, now when we talk about a domain, if we've got the xy axis and we're putting in ordered pairs, there's more to consider. So we don't just have a one-dimensional domain, we have this thing, something that looks something like this. And the points within here, these are what we're going to plug in to the function. So we're looking, first of all, we're looking at this function with two variables. And notice this has two independent variables, x and y, whereas the function we just looked at had one independent variable, x. This has two independent variables, x and y. So we pick a point over here, and we can go over and let me call this axis z. And what happens is that point will be mapped over here, like right there. Okay? And this would be f of x1, y1. And we could pick another point over here, x2, y2, and that point maybe is mapped over to here. Now this is a way we represent a function a lot of times with more than one variable. But for this function, if you wanted to look at the graph of it, if you wanted to see what's being graphed here, you realize that this z over here is the axis coming out, right? So when we look at this little domain here, we're standing above, looking down, and we see this domain. And we put in these numbers, and it sends a value up to the curve, to the surface, right? So just like over here, in the one dimension, we look at this as the distance. So like, for example, if this is the point A, then this is f of A. So it's the distance from the x-axis up. Well, down here, what we've got is when we plug in a value, it's the distance up to the surface. Okay. So we get this surface. Any questions about that? Okay, so what we want to do first of all is just consider, I'm just going to plug in some, I'm just going to look at some functions here and we can consider what the domain might be. So for example, let's suppose that I have f of xy, and let's suppose that this is 25 minus x squared minus y squared. So this is the first thing we're considering. We're thinking, okay, I know how to plot these vector valued functions. And in fact, let me go ahead, not vector valued functions, but functions of several variables. I know how to evaluate them. So let's just start off saying, well, f of 1, 2. Let's go ahead and evaluate that. See what we get. We get 25 minus 1 squared minus 2 squared. Okay, so that's going to be the square root of 20, right? Okay, so we see an output square root of 20. So we evaluate these exactly the way you would think. We put in the x, we put in the y, and we get out a value. Now, now of course, I can't just put in anything I want. For example, let's suppose I have 7, 1. Well, this is going to be 25 minus 49 minus 1. That's going to give us a negative number. So just like with these single variable functions, we're concerned with the usual things. We don't want to ever take the square root of a negative number. So here's what we're going to do. I'm going to find the domain the same way as usual. I'm going to take this, 25 minus x squared minus y squared, and I set that greater than or equal to 0. This is what I want to solve. Now I'm going to multiply through by negative, and I get this. I get x squared plus y squared minus 25 less than or equal to 0. Remember, when we multiply by a negative, we have to flip the sign, right? The direction of the inequality. And this would give me x squared plus y squared less than or equal to 25. This is the domain. Now, so this is different. We're used to saying, okay, we're used to having a domain in terms of x. Now we have a domain in terms of this. So if you look at this, though, think about this. X squared plus y squared equals 25. We know that this is a circle of radius 5. And we know that this, x squared plus y squared less than or equal to 25, that's talking about everything inside that circle, right? So x squared plus y squared equals 25 is everything on the circle. X squared plus y squared less than or equal to 25 is everything inside the circle and on the circle, right? So really the domain, you could write it this way. You could say it's the set of ordered pairs such that x squared plus y squared is less than or equal to 25. Or, really what this is saying is you can use any point that's on or inside this circle. That's the domain of that function. Okay. Any questions about that? Now, if you had something else, maybe we could have a function like this. Maybe you could have g of xy. And maybe we have 1 over 25 minus x squared minus y squared. Well, now our concern is that we never divide by 0. So with the square root, we were concerned, I don't want to take the square root of a negative number. We're dealing with real functions here. We're keeping it real. With this one, we just don't want to divide by 0. So what we want to do is we say 25 minus x squared minus y squared. That can never equal 0. Or another way to look at that is x squared plus y squared can never equal 25. Right? Okay. Well, that's everything on the circle, right? So the domain of this is everything but what's on the circle. You just can't plug in any ordered pair on this circle. Now see that? Okay. Now, let's try another one. Now, I'm bumping it up a notch. And let's suppose I have x, y, and z. Now we've bumped it up a dimension. Now, just like when we're talking about these 3D graphs, we look at the domain to be on the xy plane. Now we're talking about these x, y, and z. This has 4 variables, right? X, y, z, and w, right? I could say, well, this is w. Just like z equals f of x, y, w equals f of x, comma, y, comma, z. Now, here we have a situation. When we had 3 dimensions, we could kind of picture what the shape looked like sometimes because we're dealing with a surface. Now, our domain is going to be a surface. Okay? So now look at this. Let's suppose that we had, now these kind of problems pop up all the time. You might say, well, when will you ever have like 4 dimensions? Well, let's suppose that you're measuring temperature in a room. Well, you've got location, which is x, y, z, but what about time? Maybe the temperature changes over time. So you've got x, y, z, and time, right? So you can easily have 4 variables, right? You can easily have 4. So let's suppose that this thing looks like this. Let's suppose it is 1 over 25 minus x squared minus y squared minus z squared. Let's suppose that it's that. Now we work this the same way. We just come up here and say, well, x squared plus y squared plus z squared, it cannot equal 25. That's true. Now, what is x squared plus y squared plus z squared equals 25? What is that? Yeah, it's a sphere. So what we're saying is, okay, the domain is everything but points on this sphere. If you take any point on the sphere, don't plug that into this because you're going to get a 0. So with that, do we just put that? Yeah, you could do this. You could say x, y, z such that x squared plus y squared plus z squared does not equal 25. Okay, and you know what that means. That means that you're on nothing on this sphere. Okay. Okay. Any questions about that? Now, we get very attached in Cal 1 and 2, well, single variable calculus, to looking at graphs. So you give us a function, we want to look at the graph, and we can look at this graph and tell where the maxes and mins are, and we get very attached to that. And we can keep that attachment to a certain degree when we're dealing with functions of several variables, but we have to hold on loosely to it because oftentimes we won't be able to tell what the function looks like. Now, when we're talking about a function of 3 variables, f of x, y, we can kind of get an idea about what the graph looks like in space, but not as easily as we can with a function of just, 2 variables. So what we're going to, and when you bump it up to 3 variables, well, when you got 4 variables, then 3 independent variables, then it becomes, well, you can't do it. So let's look at this. Let's suppose that, and let me see here. I just wanted to be sure I didn't have a. Let's suppose that we have a function of 2 variables. Like that, something like that. And now, does anyone recognize what this surface is right away, though? Well, it doesn't have a z squared, right? It's a surface. What kind of surface is it? What would be 25 minus x squared? What would that be? Just in one dimension, or 2 dimensions. It would be a parabola, right? Well, 25 minus x squared minus y squared is a paraboloid, isn't it? Now, what we want, so you can see, okay, this becomes a little more difficult to visualize what's going on, but here's what we can often do. What we'll do is we'll talk about level surfaces. Level level curves. And what a level curve involves is us simply choosing values for z. In other words, I want to choose a constant over here. I'm going to say, I'm going to choose values for c. In other words, I'm going to look at different outputs that we can have for this f of x, y. So I'm going to say c is equal to 25 minus x squared minus y squared. Let's suppose we do that. And let's suppose I start off saying z equals 0. Well, if z equals 0, then what we have is x squared plus y squared is equal to 25, right? Definitely. I have that. Well, that's a circle of radius 5. So here's what we can do. We can come over here and just draw a circle of radius 5. And that right there, that's approximately it. This is a level curve. That's what that is. It's a level curve. And what it is, the z-axis is coming out from this thing. And we're looking down. We're standing on top of this paraboloid looking down. And this is one of the curves we see, right? Now, we can do this. We can say, well, I want z to equal, let's say, 9. C equals 9. Well, then what we have is we have x squared plus y squared is equal to, what would that be over here? Yeah, 16. Does everybody see why that would be the case? Okay, it would be 16. Now, this is a circle. So here we have a circle. This is when c equals 0. Now we have a c equals 9. And if c equals 9, we have a circle of radius 4. Okay, so here's 1, 2, 3, 4. And there's another level curve. It doesn't, my axis is not exactly right, but you can use your imagination, maybe a little bit. Okay, so there's a circle of radius 4. This is a level curve. And we could go on and on with this, and we could get a circle of radius 3, a circle of radius 2, a circle of any radius we want inside here. But what we would get is we would get all these level curves stacked up. And what they would form kind of a structure of the paraboloid, so that it helps us to get an idea about what the paraboloid looks like, because you can look at this and you can say, okay, when z is equal to 0 on the xy plane, here's what this graph looks like. It's that thing. When z is equal to 9, and when we raise up a little bit, you get this circle. Now, there are infinitely many of these, and you stack them up, and you get your surface. And you try to use these level curves to figure out what does this surface look like. So let's take a minute and look at this particular level surface. Here it is, right here. Here's the level surface. And let me try to turn this around, see? So I can move it around like this. Now I want to do something here. I want to get it to where we can see the level surfaces. So let me change it, and you can kind of get an idea about what the level surfaces look like, right? All these little circles, these concentric circles that they kind of pile up to make our paraboloid. Do y'all see that? See? Can you dig it? Any questions about that? Okay. So this helps us to understand what the graph looks like. That's what we use these level curves for. Now, if you see these topographical maps, you're seeing level curves, really, right? Because the map, of course, is flat, and these curves here kind of give you an idea about how the terrain is. Okay. Any questions? So there we have us some level curves. Okay, now let's look at a different one here. Let's suppose that we have this function. Let's suppose that I change the function a little bit, and I've got the square root of 25 minus x squared minus y squared. Now this is another one, and you can see that we could also generate level curves on this one, right? Now, first of all, remember what we need to be able to do. We need to be able to find the domain. And what did we say? We said the domain is inside the circle. I think we did this one a minute ago. But we said the domain is x, y, and we said, okay, x squared plus y squared is less than or equal to 25, right? Didn't we say that was the domain? So we could, realizing that's the domain, we could start plotting and finding level curves and see how this thing stacks up. And in fact, just to save time, I went ahead and did this one with Maple. I've plotted this, the square root of 25 minus x squared, and you'll notice I've got it here. And you can really see these level curves, right? Does everybody see that? Okay, so we've got two things. We've got 25 minus x squared minus y squared. I plotted that, and now I've got this one that I plotted. And you know, if you look up here, this is the angle that we're looking at. When we look from the z-axis down at these level curves, that's what we see. Now, these two graphs differ, though. I mean, you can't tell they differ until you plot them together. And here I've plotted them together. The green is the square root one, and the blue is the paraboloid. So, of course, the square root one doesn't quite have the range, right? Okay, does everybody see that? And part of the reason I did this is so you could see the commands in Maple and how those work. Any questions about that? So we use level curves to get an idea about the surface, kind of looking at the structure. We're investigating the structure and saying, okay, I believe the thing looked like this. I believe it looks like this. Well, if we bump it up a notch and we look at level surfaces, it becomes a little more difficult for us. Because now, here's what we've got. You put in an x, you put in a y, and you put in a z. You get out this fourth thing. Well, how do we plot that? The fact is, if you're trying to figure out what that looks like, you're gonna have quite a challenge, because we can't hardly visualize this fourth dimension. What we can do, though, just like we use level curves to get an idea about what how the three-dimension behaved, we can use a level surface to get an idea about how this fourth thing does. In other words, about the behavior of this. So we kind of get an idea. What we're going to do is we're going to look at level surfaces. Okay? Just like we looked at level curves, and that's the best we can do. Okay, now first of all, you realize if we're plotting something like this, what we're doing is we're still mapping over, right? You put in an x, you put in a y, you put in a z, and it maps over to something. And a lot of times we'll just call what it maps to W. Okay? So still, you put in an x, y, and a z, and you get out some number. Now, if you're talking about level surfaces, though, what you're trying to do is, it was very easy for us to picture standing on top of the z-axis looking down at the xy plane at these level curves. Level surfaces, not so much. It's hard to get your mind around it. However, let's go ahead and plot some level surfaces. Let's suppose c equals 0. Okay? If c equals 0, what do we have here? We have 0 equals 4x squared plus 9y squared minus z squared. Now, what is that? Do y'all remember what that surface is? If it had a 1 here, what would it be? Would it be a hyperboloid with one sheet? One sheet. Well, yeah, it's 1 minus. Well, what is it when it's got a 0 there? Yeah, it's one of those cones, right? It comes down, elliptical cone. Is that what they call it? Elliptical cone? Now, I went ahead. So look, you can, now imagine if I put in a 1 here, okay, or if I put in a 2. We could always get this form of this elliptical, or this hyperboloid with one sheet, right? So let me, what I've done here is I went ahead, to save time, I went ahead and cut this out. This is in your OpenStax book, this very problem, and I used that problem so that we could see these level surfaces. So you can see where we have c equals 0. And then if we have c equals 1, as we get c is bigger and bigger, it kind of opens this thing up, right? When it was 0, it was just the cone. And then we have this hyperboloid with one sheet. Okay? Does everyone see that?